Hello, crypto brohems and brohemettes. Um, I'm sorry about that. I watched the episode of Cobra Kai last night where Johnny calls some people brohems. But anyway, we have a lot to get through today, so I'm gonna just jump right into it. Some interesting stuff happening in the world of crypto. Let's just take a look at that really quick. We got the Bitcoin price, for example. Let's go. Today it's up a lot, I guess, 11%. But you've seen the volatility of Bitcoin from our second lecture. And this is really what's happening in crypto markets. This is actually leading possibly to some contagion into other markets, some interesting thoughts out there about connections between cryptocurrency and other markets right now. We know that there's some companies that have publicly traded stock that have purchased a lot of cryptocurrencies, Bitcoin particularly, but others as well. Some interesting hypotheses about connections between metals markets and Bitcoin. For example, if we take a look at the silver price, we can see that in the last sort of week or so, we had a big fall off in those metals prices. Today, those are up quite a bit, as you can see. Well, over the year, it's still like double, but we can see that there's some crazy volatility happening in markets right now. Also, in your canvas, maybe the best way, let's see what the best way to get it to this is Vice First Blockchain, because it's in my memory. I'm going to have you read this article. This is really interesting, and I think that it'll really help you understand sort of some of the logic from blockchains and help you separate some of the logic of blockchains from some of the complicated code that we have to look at. Hopefully, it hasn't gotten too complicated in terms of what you need to implement. Um, Today's is going to look a lot more complicated. I hope that it doesn't. There's a lot more going on here. I think it's pretty cool what I'm going to show you today. I'm not going to ask you to do anything crazy with code. You kind of could if you wanted to with this particular one, but there's a lot of parameters in the code that you could change to sort of play around with, and you'll definitely be asked to do that on this week's assignment. So what we're going to do is we're going to just build a simulation basically of a blockchain. So a toy peer-to-peer, because blockchains are peer-to-peer, as this section of the book mentioned. So instead of having a central authority, we work with, if I am a node in the blockchain network, or in the Bitcoin network, I should say, or in any cryptocurrency network, I'm essentially a peer. All of the others are equal to me in terms of trust and validity in that network, which is very different than traditional finance, where we all sort of put our trust into a centralized or group of centralized agents. So that's the meaning of peer-to-peer. So we will build a simplified toy version of a blockchain from a ground up. We're going to try to implement a lot of the things that we've talked about in the past, and you'll be reading about this week, namely the longest chain rule. Um, and we'll talk a little bit about how that achieves consensus in the blockchain, because sometimes we'll see that, well, what if there are two valid blocks? We already know that if two valid transactions appear at the same time, then those might be valid in different orders, but might lead to double spending. So then blocks, which show up more slowly, are the way that we get better consensus on time. However, even in that world, um, it's possible that two valid blocks are mined at the same time. And now we have two valid versions of the blockchain floating around the network. And so we need to figure out which or we need to have consensus on which blockchain will be the one that the network respects. And that is called the longest chain rule. If you see two valid blockchains appear at your node, if they're exactly the same size, then you should pick one randomly. If one's longer, then the rule is use that one. And there's good reasons that you'll read about in the book for that rule. It's somewhat complicated, but I think you can get there. A lot of times in this class, you got to stop and think about what's going on. This class is big on that, so I strongly encourage you to do that on things like proof of work and the longest chain rule. Not in terms of the computer science or the algorithm, but in terms of why we achieve consensus in this currency system that doesn't have a central agent from those rules. That's really what is important to understand. So what have we learned so far is that transactions must be ordered to prevent double spending. We talked a lot about that last week. Cryptographic hashes make data tamper evident. So if I create data, hash it, change the data in the future, that will be evident because of the tool of hash functions. Digital signatures establish authorization, which we've looked at quite a bit already, and a proof of work introduces a real cost in terms of time and computation. Here we're going to combine those ideas into a single simulation. So we're going to model blocks that contain transactions and timestamps, as you've read about. You're going to be reading the timestamp section of the Bitcoin paper this week. Proof of work is a race among multiple miners, which we've already talked about. Different miners with different levels of computational power, which the book brings up this week, and you'll be able to toy with that, and I'll ask you to toy with that on the assignment and show you in the code where you can toy with that. Transaction fees and block rewards as incentives. Why am I going to spend computational power on mining Bitcoin blocks? Well, I'll be incentivized via rewards. And ultimately, in the long run, the idea is that rewards would be, there would be no more rewards. That's what controls the supply of Bitcoin. That's why there will be a maximum supply of Bitcoin because Bitcoin is created on what's called block rewards. And I'll actually go ahead and show you that. So Blockchain Explorer, let's take a look at this block. The block reward is always the first transaction in a Bitcoin block. So we can see that that's about 3.21. Now, interestingly, let's go look at another block really quick. Doot, doot, doot. This block reward is 3.19. That's a different number because the block reward, there's a fixed block reward. It's not completely fixed. It changes over long periods of time. That's 3.15, I believe, right now. And that is those 3.15 Bitcoin are created at that moment, or I think it might be 3.125, but don't quote me on that. It's approximately, but just the block reward is the same across all of these blocks, except it does change over long periods of times. Eventually, it will decrease to zero. The reason that these numbers are a little bit higher than that is because all of the transaction fees also become part of the block reward, which you'll read about in the book this week as well. So those serve as the incentives for mining blocks and the transaction fees themselves. The reason that somebody making a transaction may want to give a transaction fee is they want to make sure their transaction ends up on a block sooner than later. Having a higher transaction fee is going to increase the probability of that. Why? Because those mining blocks are going to want to include transactions with higher fees on their block that they mine because then they'll get a higher reward. And the longest chain rule, as I just briefly discussed, restores agreement over time if we start to get two versions of a blockchain, which is called a fork in the blockchain. Because again, we can have two valid blocks. If two miners are working on different blocks that are both valid, then all of a sudden verifiers are like, hey, I don't know which one of these things to be working with. Ultimately, probabilistically, one of those blocks will eventually get longer. That will become the main blockchain by this rule, the longest chain rule. So each time we run the simulation, randomness in mining and message delays will produce a different outcome. And that would be true. Like we're seeing really only one outcome of the Bitcoin blockchain that where essentially infinite outcomes are feasible. So what we observe of the Bitcoin blockchain is one sort of iteration kind of this simulation that we're making. So the focus throughout will be why these rules lead to coordination. That's really what we're trying to understand this week and really last week. So we really understand how do these people coordinate without a central agent to do things like make new money supply, verify transactions. And remember, what we're building is a huge ledger essentially a spreadsheet of transactions over time. Because what is a Bitcoin? Why does it have value? A Bitcoin is the entire history of transactions of how it's moved around. Again, to repeat from last time, a physical coin is like that too, but we don't really need to verify anything because it's like, here it is, here's the physical coin. The fact that Gavin's holding it means Gavin owns it. I don't need to check the entire history of that coin. But in the digital world, really, so far the way that we've figured out how to do that in a peer-to-peer way is like we just will present the entire history of transactions related to this coin when it was born. It was born in a block reward. And then what happened to it after it was born. If we know that entire history, then we can have consensus on current ownership. So in this block of code, we're just defining what a block is. So we've already seen blocks have something called height. So going back, oops, I should have just kept this open. So here we go. Right here, so the Bitcoin height right now on the Bitcoin network is 935,276. And notice those just go up by one. So we're going to have a height by that. That is the height of the chain. Timestamp, of course, when the block was mined, and that's you'll be reading about why that's important this week. The previous hash, that's what creates the makes the blockchain tamper evident. We hash the previous block, and then the next block will hash the current block, and this is what creates the chain. Who mined the block? Of course, all of those blocks have transactions on them. And then the nonce is this number that we change while we're attempting to mine the block because there will be some rule. You need this number of leading zeros on your hash, and then that will be a valid, that's how we win the race to beat this rule. And that takes time, which we'll discuss right here. So the proof of work as a race. Proof of work requires miners to find a nonce, so that value we just looked at, such that the block's hash begins with a certain number of leading zeros. We saw this in last week's collab. This is not hard in a clever way. It's not like a very difficult calculus problem where it's like, I'm going to use my brain really hard and try to solve analytically this problem. It's hard in a time-consuming way. I just have to keep going until I find the right answer. So skill is not really a thing in this race, and we don't really want it to be a thing, but that's important to think about because things like new chips and new technologies maybe cause this proof of people to race faster, miners to be able to race faster. But Bitcoin, the Bitcoin network, at least not all networks, want to control the supply of Bitcoin in a certain way. So they have to adjust the difficulty of this race. When racers get faster, they need to make the race, and there's more racers too, would be another reason that they would have to do that. They need to increase the difficulty of winning the race. On the other hand, when something happens like the price of Bitcoin falls, as it has recently, fewer people should be incentivized to enter this race. So less total computational power will be thrown at this race. That will cause the rate at which new Bitcoin are being created, mining blocks, slows down. So then we need to reduce the difficulty to have the target, and the target on the Bitcoin blockchain is to mine a block about every 10 minutes. And so if we look through these numbers, and that's only updated on a temporary basis, so you could have large blocks where it's taking more than 10 minutes or less than 10 minutes, and then updates to difficulty will occur to try to get back to the one block every 10 minutes idea. And then in the long run, the average will be 10 minutes. So in the long run, the supply will behave as expected due to these changes in difficulty to target how fast blocks are being mined. Again, that's where new Bitcoin comes from the mining rewards on these blocks. And so that is how the supply of Bitcoin is controlled through the difficulty of the proof of work race. So now in the code, we just need to create miners. The mempool are the transactions that are floating around in the network that have not yet been validated by being added to a block. So it's kind of like all of these pending transactions, they've been checked for they've been verified for digital signatures, for example, but maybe they haven't been on a block yet. So there's this memory pool of transactions. Then miners will choose some of those, or they'll choose the ones most likely with the highest transaction fees, put them on a block. So then those transactions leave the mempool and go on to the blockchain. And you can read, we have a little definition of what's going on in the mempool in the writing in this collab. So we're going to say a class. You don't have to worry about that. That's a computer sciencey thing, but we're going to create this class of things called miners. And this is just the definition of what those miners are going to need to be well defined in our simulation. They are going to be able to do things like mine a full block. That's going to be based on which block do they want to mine, and then the difficulty, because we've seen that matters in the proof of work. Make a bunch of random transactions to put on the block, and then the miners need to choose transactions that they want to include on their blocks. So now we're ready to essentially make a pseudo peer-to-peer network. In a decentralized network, blocks do not appear everywhere instantly. When a miner finds a valid block, the miner learns about it immediately. Other miners receive it after a network delay. This is happening in the simulation. During that delay, other miners may still be mining on an outdated version of the chain if it forked in the past. This is how a fork occurs. Before a transaction is included in a block, it typically sits in the mempool, short for memory pool, as I already mentioned, and is shared waiting area or pending transactions, not validated transactions, or sorry, validated, but not verified via existence on a block. Are stored before miners choose which ones to include in the block. Transactions in the mempool often include fees, which act as bids for block inclusion. Because if I'm going to go look in the mempool as a miner, I'm more likely, again, to choose those transactions that have higher transaction fees. So in the next block, we can simulate peer-to-peer mining network with 3 miners, random propagation delays, and a mempool of transactions competing for inclusion. So I've already run this once. We can run it again and see what happens. One place that I want to point out for you right here, we have our different miners. We just have 3 potential miners in the simulation. In this case, we're giving 50% of the total computational power in the network to miner A, and then 25% to both miner B and miner C. Now, this will be something I ask you to play with in your assignment. All you need to do is update these to create different balances of computational power to see what happens. So let's take a look at what happens when we run this. Well, first, we can just take a look at some summary results. So miner A, the one with the most computational power at 50%, mined the most blocks. Approximately half of the blocks, which is the expected number we would think that they would mine, given that they have half of the computational power. So total payout. So canonical blocks. So remember, you could mine a block that doesn't end up actually being part of the chain. Canonical blocks are the ones that do end up on the chain. So this miner A mined 14 total blocks. 2 of those blocks in the simulation became orphaned blocks. Now we can see that they received a higher total payout from mining more blocks. But then this payout, this is the total payout had they actually achieved the block on the blockchain, but this is their actual payment because these are the blocks that actually appeared. These 12 blocks led to this payout. And so then these, of course, are the number of orphaned blocks, the ones that they mined but didn't end up on the actual blockchain. Why? Because of the longest chain rule. Something happened where two blocks were mined and there was 2 versions of the blockchain. The other miners or this miner choose one randomly to add to. One of them eventually starts winning the race. That becomes the canonical blockchain. Any blocks that were mined and added to the forked chain become orphaned. So that's where these ones come from. So look at the summary table produced by the simulation. Miners with more hash power got more blocks. Some blocks became orphaned. Only blocks in the longest chain actually count for rewards and supply growth. So money supply growth, because in the simulation, we actually can see, okay, the money supply is growing because new crypto coins, Bitcoins, are created when a block is mined and added to the canonical chain. So then we can just look at that entire chain. So the first block is called the Genesis block. And then here's the blocks that got added. Who mined those blocks? So miner B got the first block. They got a reward of 6.25 and so on. And now based on our creation, our simulated blockchain here, we can think about things like what's happening to the supply of money in this system, the supply of Bitcoins. So we can just take a look at that. Every time a block is added to the canonical block, that reward becomes a new Bitcoin. So we see these jumps over time, and those are the new Bitcoin being created. So then we can add those up. The cumulative Bitcoin created over time becomes the money supply. Let's see. So what happened to blocks and transactions? Finally, we can summarize what happened in the simulation. How many blocks were mined versus how many ended up in the canonical chain? How many blocks became orphaned? And we could have added this up from the summary table before, just other ways to look at information related to our Bitcoin that we create, or our peer-to-peer network that we created in the simulation. Um, so important limitation of this toy model that you should keep in mind, we removed transactions from the mempool as soon as they were included in any mined block. In the real system, transactions from orphan blocks return to the memory pool because like those people still want those transactions to occur. They don't want, you don't have to like go make a transaction again because you ended up on an orphaned block. In our model, we just are forcing those to disappear. That's not what actually happens in reality. And that's a nice characteristic in reality because otherwise you'd have to like, oh man, my transaction ended up on this orphan block. I actually have to go remake my transaction to get it back in the mempool. You need to do that in the simulation. You do not need to do that in an actual cryptocurrency network. So we can see this is just some information about the blocks. So we have 27 total mined, but only 20 in the actual train. Um, in the actual chain, notice that this goes to 40. This is not the number of blocks. This is time. Time from the beginning of the simulation to the end of the simulation. That's different than the total number of blocks. We could also put the total number of blocks mined there. That would be a very sort of patterned if we did that because every time it's 6.25. So that would just be a jump for every. It would be like a step function or just a straight line. Every time a block is mined, the supply jumps up. So here's just a summary. Basically, this is going to talk a lot about what I've already said, but just some summary things that I want you to take away from this and to play with and think about in the homework, in the Colab assignment. So proof of work creates costly ordering. Sorry. Mining takes time, and that time cost helps the network agree on the order of blocks, even when transactions arrive at different times. We know that can be an issue because transactions arriving at different times might lead to double spending. So we slow things down, package transactions into a block, slow things down, and then it's less likely that we get a wrong order. Even then, we might get a weird order because there are cases where blocks that are valid can show up at similar times. And then we have to implement the longest chain rule to figure out what is going to be the valid blockchain. And I shouldn't say, maybe I shouldn't use the word valid there because both of them are valid, but one needs to be chosen for the system to work. So timestamps and hashes work together. The book and the section of the paper, the paper is extremely concise. So it says insanely deep and complicated things very briefly. That's why we're reading a book in addition to just reading the Bitcoin white paper. But it's hard to kind of get this distinction from just that section of the Bitcoin white paper that time steps record when blocks are found, while hashes bind blocks to their contents and to previous blocks. Together, they create a tamper-evident history. Having a timestamp does other things important as well. Like we were just talking about this Bitcoin blockchain, we're trying to target a certain amount of time between blocks. Well, we need to know when blocks were mined in order to keep track of that. So that's just one of the important functions of the timestamp. Incentives drive behavior. So in this simulation, we're just doing block rewards so far, but don't have transaction fees. Disagreement is normal and okay. We just need a valid way of dealing with disagreement that everybody can agree is fair and helps the system work. The longest chain rule is the way we do that. Rules restore agreement, of course, the longest chain rule. And not all work is rewarded because you're going to be trying to, you're not always going to win the race, and you only are rewarded when you win the race. In the future, in this class, we're going to think about, okay, what is the incentive compatibility constraint associated with mining? Well, I'm only going to mine if the reward at least covers my computational costs, but really it needs to be more than that because it needs to be the reward times the probability that I successfully mine. So it's a much smaller than just the reward because there's going to be a relatively small probability that I win. So for example, miner A has about a 50% chance of winning any block. So they are not going to think about the whole 6.25. They're going to think about the 3.125, which is 50% times the 6.25, their expected value of getting the reward. And then we'd have to think about things like, are miners risk averse? Probably not. Are they risk loving? And then that will actually dictate their actual behavior in this economic system. That's coming in the future when we get a little bit more into the math and the sort of raw economics of what incentivizes miners more deeply. All right, so this one's worth thinking about, going through this code carefully, reading carefully, and what you read, try to think about what this Colab is doing in the context of what you read. What parts of the true blockchain are we consistent with? The true blockchain, a Bitcoin blockchain, for example, are we consistent with? Where are we deviating? And then in the Colab assignment, I'll have you play with the parameters. You don't have to change the code. You could if you wanted to, and happy to help you try to do that if you think there'd be an interesting thing to add. I won't ask you to do this, but something like put the transactions from the orphaned block back in the mempool. Is there some way to adjust this code that so we were simulating that part as well? All right, so let me know if you have any questions about this week's stuff. Um, some pretty heavy stuff in this week in terms of understanding. So remember to sit back and think. All right, I will see ya on the flip side.